Good afternoon, everyone. Today, we are pleased to welcome Mr. Stephen Wolfram, a very special guest this afternoon. Mr. Stephen Wolfram is the founder and CEO of Wolfram Research. He is mastermind behind creation of Mathematica. He was also the author of a new kind of science and the creator of Wolfram Alpha. Over the course of his career, he has been responsible for many discoveries, inventions, and innovations in science, technology, and business. Mr. Wolfram studied at Eton, Oxford, and Caltech. He published his first scientific paper at the age of 15 and had received his PhD in theoretical physics from Caltech by the age of 20. His early scientific work was mainly in high-energy physics, quantum field theory, and cosmology, and included several non-classic results. Mr. Wolfram rapidly became a leader in the emerging field of scientific computing, and in 1979, he began the construction of SMP, the first modern computer algebra system, which he released commercially in 1981. Mr. Wolfram launched Wolfram Research and began the development of Mathematica in late 1986. Building on Mathematica and the ideas of a new kind of science, Wolfram embarked on his most ambitious project to date, building a system that would make as much of the world's knowledge as possible computable and accessible to everyone. Wolfram has been president and CEO of Wolfram Research since its founding in 1987. In addition to his business leadership, Wolfram is deeply involved in the development of the company's technology and personally oversees the functional design of the company's core products. And today, he'll be sharing with us his expert opinion on the computational future. With that, I ask that you give your full attention to Mr. Wolfram and help me in welcoming him onto the stage. Mr. Stephen Wolfram. I request one of my colleagues to present sir with a bouquet.
Well, I'm pleased to be here today. It's actually, this is my first trip to India ever. I've been meaning to visit India for many, many years. Never had the chance. Thanks for organizing this event at a time when nothing much is happening in the US. Pleased to be here now. So I wanted to talk about some things that I've tried to do to kind of turn ideas into reality, to sort of create innovative technology. I want to talk about some tools that I've built that I hope will let lots of other people go through the process of turning ideas into real things. Maybe I'll start. Maybe I'll start by telling a little bit of my personal story of adventures in science and technology and so on. So as was mentioned, I grew up in England. I got interested in science and in particular physics quite young, and I started trying to do research in physics and so on. There was one problem that I always ran into, which was that in doing theoretical physics, one of the things one has to do is all kinds of mathematical calculations. And I was never, as a human, terribly good at doing all of those algebraic computations and getting all the minus signs and factors of 2 and so on right. And I said, this is kind of boring. It's very mechanical. You know, why can't I just automate doing this? Well, that was in the mid-1970s. But it got me involved in thinking about, could I just use a computer to do the kinds of mathematical calculations that I find rather boring and not terribly good at doing. So I, at that point, started to use various kinds of computational tools to do mathematics by computer. After a while, I became sort of the world's largest user of the tools that existed at the time. And then I started building my own tools to do these kinds of things. And eventually ended up building Mathematica as a way to kind of automate the process of doing the kinds of things that I wanted to do for the science that I was interested in. In building, maybe I can start off, let me start off here by showing you a little bit of what Mathematica is. At the beginning, Mathematica was kind of built as, my idea was to build a system that would sort of be the ultimate system for doing computation that I could use for the rest of my life. That was the theory. And that's worked out really well. Let me see if I can get to this here. You know, one of the features of being a software company CEO is that you always have to use the absolutely latest versions of your products. So, this is, so that means that I'll show you something which was cooked only a few days ago and will no doubt have all kinds of problems. But okay, let's see. Let's start off here. Now, actually, can people at the back see that? Yes? Okay, good. All right, that's a good start. So kind of the concept in Mathematica is to automate as much as possible of what one has to do computationally. So, you know, if we start off saying, you know, we'll say, do something like this, plot a graph. Let's say we want to make something kind of interactive here. We can say manipulate that with some parameter a here and turn that into something like this. Now we should get something where we can go and manipulate that plot like that. Or we could say make this a 3D plot. Let's say we add something here. Let's say ax plus y or something, and do this.
Could you increase the font a little?
Okay.
Okay.
Okay, so now we're making some kind of 3D plot. The general, so the idea in Mathematica is to have a general system for doing all kinds of technical computation. And over the years, it's grown from into something where we support a very large range of kinds of computation. So, for example, if I want to do some kind of algebraic computation, there's that. If I wanted to manipulate this, I could do something like this, where I say, take that and manipulate that with that parameter running from 1 to 100, and then I'll be able to do my algebra in real time here. I can. So, how do we? How do we think about? So one of the goals here is to take all of the different kinds of algorithms and methods and so on that have been developed and to put them together into a big system. One of the things that this sort of the new news. Well, let's see. I'm thinking about what I can show you here because unfortunately some of the things that I was hoping to show you are not going to work because I can't access our internal networks from here. So let me show you a little bit more about Mathematica to begin with. So one of the kind of core ideas of Mathematica is that everything is a symbolic expression. So whether I have something like this, I can say, what really is that? Well, really, it's just a plus of a power of some variable x and y and so on. That's an example of a symbolic expression. Something like this, a piece of graphics, would also be an example of a symbolic expression. And kind of the notion of the system is that everything one deals with can be a symbolic expression. And we can also just handle something that is purely formal like this. This thing can represent a piece of data, it can represent code, it can represent graphics, it can represent a document, it can represent all kinds of things. And then there are various sorts of operations that we can do on these symbolic objects. So for example, we could nest that function f like this, so we could make it so that the thing we're nesting is something that puts a frame around everything one has. That'd be the result. We can also get very different kinds of data. Let's see if this works. Let's see if I can get some, not sure if this will work, but let's see. Maybe a good sign that it's taking so long. Maybe it's a bad sign. Okay. Hopefully we can get it, no? Odd, okay. That's a bad sign. Well, I was hoping to be able to show you a nice, okay. All right, let me, what I was hoping to do was to show you an image of, let me get an image another way. So one of the things that, we can do is we can connect Mathematica to Wolfram Alpha, which I'll talk about later, but this is a good way to get an image. We can use some kind of natural language to extract information to get this image. This is probably not going to work because probably the network has failed here. Oh well, okay. Oh dear. Okay. Let's see whether anything's working here. Ah, that worked. That's a good sign. Well, let me try to yeah. Okay. What I wanted to show. Let's take this and make it into an image here, and then I could do something. What I was trying to show you was that this thing I can treat as an image, and for example, I could say let's blur that image here, and we can get something like that, or we could say something like make a nested function where we just keep blurring this image over and over again. So I could go like this. I could use the kind of operations that I was using before to just go ahead and progressively blur the image that we had. So the thing that's significant here is that we're taking all sorts of different kinds of things, whether they're algebraic expressions, graphics, images, whatever, and we're able to manipulate them using the same underlying symbolic language. And for example, we could do the same thing if we take something like we take some kind of network that we create. We could say something like this, and that will have some mapping, and we could say show this as a graph, and then we'll be able to take that that thing now as a network, and we can do operations on that network and so on. Well, so one of the things that as we've tried to build up Mathematica, it's progressively, we've added a huge number of kinds of functionality. The thing that has emerged in recent times is that the language inside Mathematica has grown far beyond what has sort of been progressively building, and we're now sort of breaking it out as a separate construct that we call the Wolfram language. And the kind of the idea of the Wolfram language, it's sort of a different direction that other computer languages have taken. When you think about languages like C or Java or Python or something like that, the languages are intended to be kind of minimal. They just give you some basic operations of the machine, and then if you want to actually have algorithms and things in the language, you either have to build them yourself, or you have to use some libraries that somebody has constructed for this or that algorithm. The idea in the Wolfram language is to build a kind of knowledge-based language where all of the kind of algorithms that you might want to use are, in a sense, building blocks already built into the language. And this is something where sort of it's a different concept, because we have something where the language itself already has lots of knowledge built in. So these are some sorts of categories of things built into the language, whether it's machine learning or statistics, or whether it's things for doing string manipulation and so on. And one of the big challenges in building this language is to keep all the pieces of the language coherent and consistent. And for the last 25 years, which is the time since Mathematica first came out, it's been one of my personal big efforts to try and maintain kind of a high degree of consistency between what are now the 5,000 or 6,000 sort of built-in primitive operations and algorithms in the language. Actually, what's happened in recent times is all sorts of kinds of things have happened as we've kind of built up this huge web of algorithms and capabilities. One of the things that's been interesting to me is one used to think that if one wanted to do some kind of numerical operation or something like this, that one would be best to use some special purpose numerical computation system that was particularly built to do, let's say, matrix manipulation or numerical integration or something like this. But in fact, and one could expect that there'd be sort of an algorithm for numerical integration which could be specified just as an algorithm for numerical integration. But the thing that we found in the last probably 10 years or so is an increasing trend towards the best algorithms being ones that make use of huge other building blocks. So even though you think you're setting up an algorithm for numerical integration, in reality, you have to use things that are nothing to do with numerical computation. You have to do, let's say, algebraic preprocessing of the integrand that you're integrating. Or you have to use some piece of combinatorics or graph theory or computational geometry or something to do the algorithm you want to do. And so we found ourselves in sort of a unique position to be able to create the most efficient algorithms that can be created because we have all of these different building blocks from all these different areas of algorithmic work built into our language. So increasingly, the modern algorithms that we create are ones where the building blocks are based on lots of large areas of functionality. That's one kind of interesting trend of sort of development of the system. Another thing is that we've been interested in kind of making everything as automatic as possible. So kind of the role of the user is to define what their objectives are. The role of the system is to figure out how to achieve those objectives. So for example, let's say you're doing, I don't know, you're dealing with graphs and you're interested in, there's a question of how do you actually display those graphs? Well, it's the responsibility of the system to automatically kind of do the computational aesthetics to figure out a good way to display the graph. And that notion of automation carries through in lots of different places. So for example, going back to the example of numerical integration, there might be 400 different algorithms that our system intrinsically knows about for doing numerical integration. There's the question of, for the particular computation that you're doing, which of those algorithms should you use? And so what we've increasingly worked on are sort of meta-algorithms that will automatically choose between the different possible algorithms that can be used for a particular problem. And so that's, again, another kind of general trend of the kinds of things that we're doing is to automate as much as possible and to create meta-algorithms that will automatically select between sort of the underlying algorithms one's dealing with. Well, one of the things, so in building the Wolfram language, one of the objectives is to have a precise language for describing algorithmic kinds of work, where the sort of primitives of the language represent the kind of repeated lumps of computational work that one needs to use. Well, a number of years ago, based on what, yes, that worked. So, in a sense, the Wolfram language is about, Mathematica has traditionally been about sort of precise technical kinds of computations. Well, as a result of a bunch of science that I did, which I can try to explain to you a little bit, I realized that there was sort of a possibility to do something that was, in a sense, more, in a sense, a broader footprint in terms of what it tried to handle. And that got me involved in the Wolfram Alpha project. And the idea of Wolfram Alpha is to try and make sort of as much of the world's knowledge as possible computable. So what that means is there's all sorts of knowledge that has been systematically collected in the world. The question is, can we set it up so that if there's a question that can in principle be answered from that knowledge, we can make it automatic to get the answer to that question. So for instance, so the idea is, you type in a question, you say, what is the integral of, x cubed cosine squared x? And hopefully, if we're successfully connected to the network and so on, we'll get a result there. And kind of the idea of Wolfram Alpha is to not only give us a result, but also give us kind of a report that shows us other kinds of things that we might find interesting. So it's telling us alternate forms of the integral, expansions of the integral, and so on. And you can also ask it to show you a step-by-step version of this integral. This is something that, one thing to explain about the step-by-step solution is that it is completely fake, in the sense that the actual way that Wolfram Alpha and Mathematica and the Wolfram language underneath compute the integral has nothing to do with the presentation that's given here about how a human might solve this integral. But this is real useful to a human who wants to do the integral. Actually, I see here something that's fun. This is a very recent thing that we introduced, which is a sort of an inverse to Wolfram Alpha, something where instead of instead of Wolfram alpha computing the answer to an integral that you've asked it to do, it's going to generate an integral to ask you as a human to do. Actually, it turns out to be really hard to generate integrals that have certain ranges of difficulty for humans. It's actually, in many ways, harder to figure out what integrals you feed to a human than it is to do the integrals in the first place. But so Wolfram alpha is a free website. There are also mobile apps for it and so on. It's also the system that's used inside, for example, the Siri intelligent assistant from Apple and the S-Voice assistant from Samsung and so on, to produce answers to kind of knowledge-type questions. And kind of the idea of Wolfram alpha is it covers not only kinds of technical questions like what's the integral of something, but also other questions like, you know, what is the population of India, let's say, which is a hard question. And all we can do is to report what the UN and other people say. Is that right? Who's to know? Oh, look at that. That's the long-term history. So, you know, one of the objectives of Wolfram alpha is to, well, let's ask some other questions. Let's see what let's see. Actually, let's ask this question. Let's see whether we can do that. Oh, it doesn't know. Well, I'm shocked by that. Let's see whether maybe it will. Okay. It has some estimate for that. Do you think that's right? Oh, it's from, you know what, the reason why it wouldn't do the previous thing is because the data that it has for Mumbai is pretty old. It's from 2004. So it wasn't prepared to combine that with the data that it had for all of India. But we can say, here's the thing we can ask. It's always an interesting thing when you build a giant software system and you can ask it questions where you can, in principle, just look out of the window and see whether it's giving you the right answer. So here we just asked it, what's the weather in Mumbai? And it will give us all kinds of data about that. This is showing us the temperature as a function of time for the last few days. And it seems to be warmer during the day, colder at night, which is kind of what we would expect. It's getting this data from the nearby airport and so on. So the thing that, so there's all kinds of data. I don't know, if we ask it, let's say we type in something like ISS, which it will interpret as meaning the International Space Station. It should be able to figure out something like where the ISS is right now. It'll tell us, for example, down here probably, it'll tell us that the ISS is not currently visible from Mumbai and so on. Well, we can go on and let's say we type in something like this. We could say, type in something like that. It'll assume that that's a piece of the human genome, and now it'll probably go and try and figure out where in the human genome that particular base pair sequence occurs. So it gives us some results there. We go and go and ask it some more details about that particular kind of thing. Or we could do something. Let's do something completely different. Let's ask it something like this. This is some more engineering kind of thing. This is probably a type of airfoil. Let's see whether it knows. See what it knows about that. And it's telling us it's computing for that particular type of airfoil. It's computing various kinds of technical engineering properties of that airfoil. There, it's got some results for that. Let's try. Maybe we can try some other area of engineering. Let's try. Well, we can try something about chemistry. We can say something like, let's try something very straightforward like methane. It'll probably give us all sorts of properties of methane. Here, actually, let me show you something more interesting that we can do here. Let's say we say methane, 26 degrees centigrade, 2 atmospheres. Let's see whether it can compute the thermodynamic properties of that substance. Okay, so there we go. So it says that at 26 degrees centigrade and 2 atmospheres, methane is a gas. it has this density, this sound speed, there's where that lies in the phase diagram for methane, and so on. So we've been, in building Wolfram Alpha, we've been trying to sort of encode as much knowledge about the world as possible. We could say something like, we could ask it about some movie. What's a recent movie?
The Wolfram Wall Street.
What? Let's see what it knows about the Wolf of Wall Street. It's not a movie that I've seen yet, but let's see what it knows. Okay, there we go. So it was released 10 days ago. This is US box office data, so it says it's made $34 million as of December 29th, and so on. It can give us some. So it has a certain amount of information about this movie that came out a couple of weeks ago. So we can say so kind of the concept in Wolfram Alpha is to sort of ingest as much information about the world as possible. So there are many different categories of, yeah, let's try something that, let's try something like, let's see whether we can do this. I have no idea whether we'll be able to do that. Is that right? There are all kinds of things that we're trying to encode. Let me pick some other kinds of areas of engineering. So, for instance, we can do all sorts of, I don't know, let's do something in control theory. Let's say, this is just an example, that find a transfer function for this particular algebraic thing. Okay, there we go. So we've got, this is doing standard control theory kinds of computations. I think it's really cool that one can just go to a free website and get computations like this done. And I think it's also remarkable that you can just on a little tiny phone or something, you can get to do all of these kinds of very technical computations. So I might mention something about what's actually involved in making a project like this work. Underneath, it's all the Wolfram language allowing us to actually encode all of this kind of knowledge and all of these kinds of computations. But there's several steps. One thing we have to do is get lots of data about lots of kinds of things in the world. And that's something where you might think, well, the web is big, it's got lots of data on it, we can sort of forage this data from the web. That turns out not to work. The web is just too inconsistent, too messy to be able to do that. Instead, what we've ended up doing is going to the sort of primary sources of data for thousands of different kinds of domains of data and working with the people and organizations that have created those primary sources of data, and then taking that data and curating it and understanding what the data means and making it computable. And the first step is you get all the underlying data. And by now, we've got many tens of terabytes of data. We have more data that flows in every second into the system. The first step is to get all of that underlying data. We've got actually by now significantly more data than the complete text content of the internet in terms of just raw data. So even if we were to take the whole, even if all of the text of the internet was usable as computable data, there would not be enough of it to provide what we need for Wolfram Alpha today. But so even given that we have the underlying data, it turns out that people typically don't just want to know some individual number from some collection of data. They want to compute something based on underlying data. And so for that, we have to do something else, which is to look at all the different methods and models and algorithms that have been developed in science and engineering and financial analysis and lots of other kinds of areas, and encode all of those algorithms in such a way that we can make use of them. And it's sort of an interesting process because in all these different areas, we've been trying to get it to the point where we are doing sort of the best research level computation of any kind of thing that one wants to compute, whether it's about medicine or engineering or financial analysis or whatever else. And by now, it's about 15 million lines of Wolfram language code that represent all of those methods and models and algorithms inside Wolfram Alpha. Well, the next problem is, okay, so we can compute all these kinds of things inside our system. How are humans supposed to tell the system what to compute? Well, with a system as broad as this, really the only form of communication that's viable is human natural language. And so we've had to develop a system which can which can understand human natural language as people present it, as people type it in, as people speak at the phones, and so on. Actually, that problem has been a difficult problem that people have been working on for a long time. We've had an amazing advantage relative to what anybody else has had in the past, which is that we have all of this knowledge built into our system. So when we try to understand natural language, we're doing that understanding on the basis of lots of built-in knowledge. And that's why we've been vastly more successful than anybody has been before at being able to actually understand natural language that's being input. Well, let me, so the kind of the concept of Wolfram Alpha is being able to do computations about lots of kinds of things in the world. One of the things that's really interesting that is just now happening is in the Wolfram language, we're actually making it possible within the context of this precise language to do computations about the world. And so built into the language are things like, let's see if I can get this to work. Let's say something like this. We're using natural language here. I hope this will work. May not. We're using natural language here to kind of specify something that is going to become a precise construct in our language. This may not work. I don't know why the. Oh, I see. Wow. That was very bizarre. That's very, very strange. It's something to do with a proxy server. Oh, you can enter a password for a proxy server. Okay, that's cool. All right, go ahead. Go ahead. You get one. I think you have this. Okay. There you go.
Can Mathematica figure out the password in that?
No. Okay, let's try this again. Let's see. Let's bring up the same dialogue. Did you say? Sorry. Try one more time. This doesn't work with the ones. Ah, very good. Okay, let me show you something else that we should now be able to do. In the Wolfram language, we have sort of a precise computer language. But what we can do is to use the kind of natural language understanding capabilities that we built for Wolfram Alpha to do sort of natural language programming. So I just said, plot a cosine curve, and then I'll get this, and I could say sort of add a purple frame to that. And now what will happen is that we'll be sending that piece of natural language to our servers, and we'll figure out from that natural language, we'll essentially synthesize a piece of code that executes that operation. And now what I was going to show you before is something like if I say countries in Europe or something, then what should happen is that I will get these things out that are entities that represent countries in Europe, which I can now do computations with. So I could say something like, entity value of that, comma flag. And what should happen now is that it'll go and try and compute for each of those entities what are the flags of those countries, and I can say something like. Actually, let's try this. This might be kind of cute. Let's see if we can. There we go. So there's a collage of all those flags. So we could go and say something like we could go and take these flags there, and we could say let's do edge detection on that collection of flags, for instance. And again, we can actually. It's kind of an interesting case where I can show you that we just take in the Wolfram language, we just take a thing like this, as I was showing before, and we just can use it as symbolically as a piece of a function to do a computation. So anyway, one of the things that's interesting that's happening is this kind of merger of things about the world at large and representations of the world at large and the precise language that we have in the Wolfram language. And there's a thing we call WDF, the Wolfram Data Framework, which is something that's coming in the next few months, that's kind of making use of the whole ontology that we built up in Wolfram Alpha for describing things in the world. So within Wolfram Alpha, we know about all the different chemicals and movies and species and cities and so on. And this is a thing where we're making it possible for anybody to take data that they have and convert it to this WDF form so that there's a kind of precise representation, a precise semantic representation of that data. And this is something that's important for being able to do lots of kinds of data science work, and we're building all kinds of technology to do that. One area that I might mention, that direction that we're going in along those lines, has to do with connected devices. So some of you might have seen an announcement a couple of weeks ago. Let's see whether I can find this. Well, let me just mention that one of the things that we are now trying to curate, in addition to curating knowledge about the world, we're also interested in curating interfaces to the world. So we're interested in curating APIs that exist in the world. We're interested in curating devices that exist in the world. I'm afraid I'm probably not going to be able to get to this, but in about 2 days, there'll be, on the public web, there will be a thing called devices.wolfram.com, which I'm not going to be able to get to this. Unfortunately, we can't get to the, no, it's not going to work. Sorry. Otherwise, I could show you something cool there. But what we've been doing is trying to curate all the different kinds of connected devices that people have been developing. There's about 1,000 different kinds of devices that we've been dealing with that are things for measuring health kinds of things, things for measuring physical properties of materials, all sorts of other kinds of things. We've been sort of curating the properties of these devices, and the first thing that will happen is our connected devices project is supposed to go live in a couple of days, that shows properties of these devices. Then that's kind of a precursor to the next step, which is to provide a general framework for connecting to all these kinds of devices from within the Wolfram language. And that's something that we've started to do. And so, for example, if I go and show you, I could probably show you, let's see. So a typical kind of thing, let me just pull up here, the kind of thing we're talking about. Typical kind of thing, I don't know if you can see this, but there are operations like device read time series. So given a device, we can read a time series from that device and then be able to compute from it. And so the notion is that we curate these different kinds of devices and we sort of automate the process of being able to access information from these devices. So something which has happened recently is that our language is starting to be able to be run on smaller and smaller and more ubiquitous kinds of devices. So one thing that happened recently was we announced that we're making the language available freely, actually, on the Raspberry Pi Linux machine, which you can get for $25 in the US. This is a tiny little board that runs Linux and also now runs the Wolfram language. And so you can basically embed the Wolfram language inside of all kinds of devices and use it to control your robots or whatever else. So now another thing that, the big thing that's happening is we're sort of, one of our goals is to make this Wolfram language a knowledge-based language accessible as widely as possible to people, and not only to humans, but also to machines. So one of the things we're also doing is that the language is something which typically has run inside an individual computer and so on. We're also setting it up so that it can run in the cloud. And we're setting up our Wolfram engine system, which is the thing that drives Wolfram Alpha, for example, to be a generally cloud-accessible thing. And again, I'm unfortunately not going to be able to show you this, but I'll describe at least what will soon be possible. So I showed you kind of interacting with Mathematica and having this session where we're just doing computations. You'll be able to have the same kind of session interacting with the Wolfram language in the cloud, where you just have a web browser to do that interaction, and all the computation is happening in the cloud. And in fact, those things where I was doing interactive manipulations and so on, you'll be able to make the technology that we have that is what we call computable document format, which is what lets us do all of those kind of in-document computations. That technology will also be available on the cloud, so we'll have a thing called Cloud CDF, where you can have one of those little interactive computations going on, and you can put it on any website you want, and it will call our cloud to do the computation. Okay, so the place where things get kind of interesting in the cloud is you'll be able to do the following kind of thing. We're going to have a thing we call the programming cloud, where you write a little program in the Wolfram language, and typically Wolfram language programs can be very short because there's lots, every line does a lot of stuff. Given that tiny little Wolfram language program, you can then say, okay, I want to deploy this program as an API in the cloud, or as a form-based app in the cloud. And so by just essentially pressing one button or running one command, you can take this little piece of code that you've created and you can make it accessible to everybody through the web. So this is pretty interesting because it means that if you have some kind of algorithmic idea which you can implement in the Wolfram language, then you can immediately take that idea and deploy it. Kind of the idea is to be able to universally deploy things that have been created in the Wolfram language. So the notion then is you can deploy, you can create an API that people can call from anywhere on the web and embed inside their own programs. You can actually set it up so that your little piece of Wolfram language code is called from a random Java program or something through a sort of function call interface. You can actually also set it up so that you have an embedded version of the Wolfram engine where you take the whole Wolfram engine and put it on the same computer that you're running your Java code on, so that you can then basically call the Wolfram language from inside any other kind of system. So there's lots of kind of plumbing that has to be connected together. Lots of things have to work in order for this to be possible. But what's exciting about it, as far as I'm concerned, is it takes this kind of knowledge-based computing and it lets it be deployed all over the place. It lets it be deployed in websites, in mobile apps, in all kinds of other places. It also lets it be deployed inside embedded computing systems and so on. And so I think the picture that we have right now of saying that it sort of is about to become kind of a very widely accessible resource to just be able to assume that you have knowledge about the world and assume you have all these algorithms for computing things included within the language that you're using to do things. Well, I thought maybe, I'm not sure how much time I've no clock, so I can't even tell how long I've been going on here. Well, let me maybe I'll talk just for a few minutes about some basic science that that was sort of part of the original motivation that I had for creating Mathematica in the first place, and that is now feeding back into all sorts of technology kinds of things. So one of the things that I got interested in probably 30 years ago now was the question of when we look at things like the natural world, we see all kinds of complex behavior in it. When we think about how we model the natural world, the method that we've been using for the last 300 years mostly has to do with let's use math and mathematical equations to find models of what happens in the natural world. And that's an approach that's been really successful for lots of purposes in physics and engineering and so on. But there are plenty of systems in the natural world which we haven't successfully been able to model using sort of traditional mathematical methods. So I got interested in how do we generalize what's been done in kind of mathematics, and how do we build more general models of the world. And so what I realized is programs are a sort of more general kind of modeling that one can do of the world. But the question is, what, when we think about what kinds of programs might be models of the natural world, they're probably not the kinds of programs that we're used to writing, thousands of lines of code or whatever else. They're probably very simple programs. There's sort of a basic science question, what do simple programs typically do? And let me try to show you an example here. Let me see if I can make this work. Oh, come on. This is very challenging for me, getting the computer to do the right thing. How am I going to get this to go on the right screen? Okay, one more problem to solve. Let me see if I can do something here. All right, I get improvised completely. Okay, let's. I'll tell you what. The question is, what do simple programs typically do? We could actually do an experiment using the Wolfram language, using Mathematica to try and answer that question. So let me show you an example here. Actually, I'll tell you what. Let me start off by going to Wolfram Alpha and showing you kind of the basic idea here. So the question is, what are some typical examples of simple programs that we can use to kind of study this question of what does simple programs typically do? So a class of programs that I've studied a lot are look at that, Wolfram Alpha figured out that we were talking about stuff related to my kind of science. So it gave us a nice ad for my book on the right-hand side. A particular class of programs that I've studied a lot are some things called cellular automata, and they work in the following way. They just have a row of black and white cells, and at every step, what happens is that the color of each of the cell on the next step is determined by the color of the cell itself and its left and right neighbors on the step before. So you can kind of encode a little program here that says what that system should do. Well, now the question is, well, what happens if we look at different kinds of different rules of that general kind? So let's say we look at say we do this. And I'm just writing a piece of Wolfram language code that will just compute what this program does. Okay, there we go. Okay, so here's an example of a slightly different underlying rule. We start off from a single black cell at the top, and we get this checkerboard pattern. Well, now let's try another rule. I happen to know rule number 90 makes a pattern like this. And which is quite an intricate pattern. If we continue it a while longer, we'll see it makes this whole nested kind of pattern. But it's still a simple rule, intricate, but nevertheless rather regular pattern. Okay, so now we get to do a little experiment. Let's say we want to look at what the patterns that we get from all possible rules, let's say the first 64 rules of the general type we're talking about here. So we can do this. Actually, I'll tell you what. Let me do the following. Let me say, no, that's not what I wanted to do there. That was very confusing. There we go. Okay, so what this is showing is every picture corresponds to a different one of these underlying rules. So what we're seeing is that with most of these kinds of underlying rules, the behavior is extremely simple. fraction of the algorithms that we're adding are algorithms that we didn't invent as humans kind of step by step, but instead we discovered by mining them from the computational universe and saying we need an algorithm that has this and this property, let's search 1 trillion possible programs to find one that behaves in the right way. And what happens there is that we end up with these hard for humans to understand, but highly efficient and sort of highly original algorithms for different kinds of things. And that's an approach that I think we're going to see increasingly. Well, I might say that this whole notion that all the different things this notion that computation is more widespread in the world than one might have expected is an important notion. It's a notion that has lots of implications for all sorts of things, whether it's for sort of philosophical questions about free will, or questions about extraterrestrial intelligence, or questions about sort of the future of the human condition and so on. Lots of different topics that are kind of addressed by this sort of discovery that computation is more ubiquitous in the world than one might have expected. I think also that one of the things we realize as we look at sort of the progression of technology now, and the kinds of things we're trying to do with the Wolfram language, trying to sort of inject sophisticated computation into everything. One of the things one realizes is that there are now maybe 10 billion computers in the world. The number of computers in the world is going to progressively increase, and in fact, probably before too long, almost everything will effectively just be made of computers. In a sense, everything will become programmable. Everything will be able to be to compute. We'll be able to control the computation of everything, and we'll have this environment in which everything is computational and programmable. I should probably stop here because I think I've gone on much too long, and I'd like to get questions from people and discuss whatever topics people would like to discuss. So thank you very much. So please, yes.
If Wolfram Alpha was to go head-on against IBM Watson in Jeopardy, who would win?
So I'll repeat the question. So, as Wolfram Alpha was competing with IBM Watson and Jeopardy, who would win? We would lose. Actually, we might not lose because they're about. We should lose because what we're doing is something completely different from what Watson is doing. Watson is a text retrieval system, and it's been fed lots of stuff from Wikipedia and the web and so on. And its goal is to take, the clues from Jeopardy and try and match those clues using text retrieval with the corpus of data that exists there. And in fact, I did an experiment when the Watson project was going on of just use search engines to just search the web and use the and for the 200,000 Jeopardy clues that have been used so far, and ask the question. 200,000 or 20,000? 200,000. Ask the question, how often can one get the correct answer for Jeopardy just using a search engine on the web? And the answer is 80% of the time, the first page of search engine results contains the correct answer. So it's a text retrieval problem, and that's completely different from what we're trying to do in Wolfram Alpha. In Wolfram Alpha, we're computing fresh, new results every time somebody asks us something. And in fact, when we look at the Wolfram Alpha website or at Siri or something like that, the vast majority of questions people asked have never been asked before. So nobody ever wrote them down on the web because they've never been asked to us before. They don't exist on the web. What we're trying to do is something, in a sense, much more ambitious than something like Watson or a search engine. We're trying to actually encode knowledge in such a way that we can compute fresh information, fresh knowledge from what's there, rather than just retrieve existing knowledge. Now, there's a sort of merger of these two ideas, which is to take things like the web and view them as data sets that you can do data science on. And we get to do a pretty interesting form of data science because we already know a lot of things. We can already compute a lot of things about the world. So when we look at something like the web, we can know, when there's an entity mentioned on the web, we know what this means, and we can start to compute things from it. So there's sort of a combined approach to doing sort of text retrieval and computational knowledge that I think you'll probably see some interesting things in the next couple of years come out on the basis of. Yes, please.
The notion of computing is generally associated with the idea that there is a universal truth to some sort of question that we're asking. This sort of contradicts with what we see in real life, where sometimes people who are dumber finish ahead of people who are smart, and inconsistent information seems to be the order of the day. How do you reconcile this particular phenomenon?
Well, so there are a couple of different issues. I mean, so one question is, when we're dealing with things in Mathematica or in Wolfram language that are precise algorithmic kinds of things, you compute, there's definite rules for the computation, you hopefully get the right answer, it's all very cut and dry. When you're dealing with information about the world at large, there's the question of, do we correctly know the population of India? Do we correctly know, the GDP of some country? These are things which it may be very hard to actually know for sure. Somebody's got to go out and take a census. It's hard to do that. The answers may not be correct for one reason or another. What we've done in Wolfram Alpha is we've taken the point of view it's better to give some information than no information. So, for example, lots of kinds of socioeconomic data. We'll use data from the World Bank or the United Nations or whatever else. We are well aware, we know the people in those organizations quite well. We're well aware of the fact that everybody knows that data isn't perfectly correct. But it's better to give some data that you can do computations with, comparisons and so on, than to give no data at all. And we try in Wolfram Alpha to show the source of data that we have and so on. Now, if you ask a more fundamental question about whether one can compute useful things in the world, I mean, I suppose the history of science and technology is kind of gives us a pretty good indication that it is useful to compute definite things in the world. It's not, there are plenty of one of the things that's been a surprise to me actually, the Wolfram Alpha project, is the extent to which things that I thought were qualitative facts about the world, subjective facts about the world, actually have sort of a hard computable content. So, for instance, if you go and look at, you go and compute something about, let's say, let's pick let's say something like Macbeth, the Shakespeare play. Okay, you might think there's nothing to compute about this. It's just some work of art. There's nothing computable about it. Well, actually, there is. There's sort of metadata about the play. Then there's the actual structure of the play, how many words are in it, which words appear, which characters there were in the play, what's the time series of occurrences of a particular character and so on within the play, those kinds of things. A lot of things that we think of as purely subjective and qualitative seem to have some kind of underlying computational, we can compute something with them. Now, I'm not quite sure, I mean, in terms of the question well, I'm trying to interpret your question in a variety of different ways, okay? I'll give you one more interpretation, okay? A quite different interpretation, that in the area of mathematics, okay? So one of the things that I've been, as we look at simple programs out in the computational universe and so on, one of the features of those programs is that lots of questions you might ask about them end up being undecidable. You ask a question like, will this particular behavior in this program will it ever die out after an arbitrarily long time? There may be no finite procedure that can answer that question. It's kind of a Gödel's theorem-like situation. So it's really common in the computational universe to run into questions that are undecidable. So a question that one might ask is the kinds of questions that humans tend to ask in, for example, mathematics. Why are they actually answerable? Why is mathematics doable? Why is it the case that the questions people have chosen to ask and answer in mathematics can actually be answered rather than just running into undecidability all over the place? And so I've been sort of interested in this question. I talked about enumerating possible simple programs. You can look at the axiom systems that people have used in mathematics. The axiom systems people have used in sort of the historical mathematics that's been done are a pretty small set of axiom systems. And you can ask, what about all the other possible axiom systems? And I unfortunately can't show you pictures here, but because for some reason this isn't working quite right. Let me just try one thing. Yeah, look at this. This might work. Okay, I'm gonna. It reveals the method, but let me. Here we go. So I can show you. Let's see. This is oh no, hopeless. That. Okay, one more try. Anyway, what I was going to say was that one of the things that's interesting. There we go. Okay. So that's an example of that's a single-page version of the axioms that get used in mathematics today. And there's a question of what happens if you just sort of start enumerating axioms at random. What do they typically do? One question would be when you look at axiom systems that people have been interested in, like Boolean algebra, where do those lie in the space of all possible axiom systems? So this is an example where we're starting off from kind of the typical axioms that you might find in a textbook of logic. And it turns out that in this sort of space of all possible axiom systems, something I discovered a number of years ago is that actually you have to go through only maybe 50,000 axioms before you find one that will reproduce Boolean algebra. So this is telling you in the space of all possible axiom systems, where does the one for the thing we've studied, Boolean algebra, lie? And the answer is it doesn't lie too far out in the space of all possible axiom systems. And this tells you something about sort of how the mathematics that we've chosen to study is distributed in possible mathematics. It's sort of dotted around at different places. In any case, so the thing that so there are these questions about sort of why isn't there more undecidability in mathematics? The answer is, I think, that mathematics has grown in a very historical accident kind of way, sort of specifically navigating through those parts of sort of the space of all possible mathematics where it is possible to know things as definitive truths. Go on, other questions? Yes, please.
I have two short questions. First one, rule number 30. Is it possible to reverse the effects and find out what the rule was initially for any of the rules?
So some cellular automata are reversible. So given a particular final condition, there's a unique initial condition that corresponds to that final condition. Most, like Rule 30, are not reversible. The ones that are reversible are kind of interesting because they're very much like what happens in physics, where one thinks about thermodynamics and mechanics and so on, and one thinks about mechanical processes at a microscopic level are reversible, but at a macroscopic level we have things like the second law of thermodynamics, law of entropy increase. You can see that kind of thing happen when you look at reversible cellular automata. But Rule 30 is not a reversible rule. You can also ask the question, if you're given the center column of values in Rule 30, can you reconstruct the particular initial condition that was used? That's an important question when people use Rule 30 for cryptography. And the answer is, it is very hard to, it is probably an NP-complete problem to reconstruct the initial condition given the sequence. It has not been proved to be NP-complete. In more complicated cellular automata, it can be proved to be NP-complete. It's a really interesting question whether it can be proved for Rule 30. We don't know yet.
It's an open problem.
What's that? That's an open problem, yes.
And another thing is, would the Wolfram alpha's natural language processing engine be available on a locally hosted cloud sometime?
Okay, so question, the answer is there's going to be a private, well, there is actually now an appliance private cloud version of Wolfram Alpha. It's a thing that, so Wolfram Alpha, the one that you get to see for free on the web is based on public knowledge and public data. We have built quite a large number of private Wolfram Alphas for large organizations and companies and so on around the world that make use of not only our public data, but also their internal proprietary data. Those custom versions of Wolfram Alpha are all based on locally hosted Wolfram Alpha clouds. In fact, the general thing that's going to happen is, first, the Wolfram language and Wolfram engine, there's going to be a cloud version of that, both with our cloud, and there's going to be a private cloud version of that. Those are slightly easier to host than a Wolfram Alpha local cloud, because Wolfram Alpha is a pretty complicated creature. Not only does it have to deal with lots of computation and data, it also has to deal with lots of real-time feeds coming into it. And it's not quite so easy to get all of that stuff set up in a way that's just a box. But you can, larger organizations do buy Wolfram Alpha appliances, which are racks of equipment with a bunch of connections that are essentially locally hosted versions.
So most of the data is explicitly tied into the database, or is there a method that you generally use to pull data?
So the data that's the data in the generic Wolfram Alpha is all data that's that we've curated, that we've got from primary sources of data and so on. There is also within Wolfram Alpha, in fact, you can actually upload data. So in the public version of Wolfram Alpha, you can do a certain amount of you can take some piece of data, you can upload it to Wolfram Alpha. This is in the pro version of Wolfram Alpha, and it'll try and tell you interesting things about that data. In the actually one of the applications of this, let me show you one thing here. Okay, so this is just a sample data set, and it was a piece of tabular data, 650 rows, 2 columns, and this was something, I guess this is some email data set or something, that shows you what it did was, given that data set, Wolfram Alpha tried to automatically figure out what's interesting to say about that data set, and it gave us these kinds of results. Actually, I might mention one of the types of data sets that you can feed to Wolfram Alpha is a Facebook, is going through the Facebook API. Something that's quite amusing. Let's show you something. So, for example, a lot of people used our Facebook analytics in Wolfram Alpha, have used it over the past 6 months or so, and we can now go and take all that aggregated data and figure out things about the world. Like, this is the distribution of the ages of friends for people of different ages. So, for example, if you're 20 years old, the vast majority of your friends on Facebook are right around also 20 years old. If you're older, the distribution, you have a broader distribution of friend ages. And then you can figure out all kinds of things. Let me show you another kind of cute thing you can figure out. This is from Facebook. This is dominated by US data here, but we can slice it down probably for Indian data too. This is as a function of age. This shows probabilities from male and female to be in different relationship statuses. And actually, what's interesting about this is that the data follows. If you compare this for US data, if you compare it with what the Census Bureau measures in the US, Facebook is a remarkably good proxy for what's measured by the census. Let me show you one other plot here. I'll show you a plot. This is a plot of this is a plot based on Facebook of people, how people move from one hometown to one current residence. So it's showing you between different countries, it's a flow of people from one country to another. So you can see some things there. I guess there's a big US flow. In other countries, there's a big China to US flow. In any case, these are things where we're dealing with data that's uploaded to the system, and that's kind of one slice of using Wolfram Alpha in the local way.
Unavoidable time constraints will conclude our program here. Thank you so for spending your precious time with us and enlightening us over the